Good evening, guests. Riaan allemaal. Can you please stand as the procession is about to enter the venue? Thank you.
Please read it. Goedemiddag, dames en heren. Good afternoon, ladies and gentlemen. So, just to briefly introduce myself, my name is Wikus van Niekerk, and I'm currently the Dean of Engineering here at Stellenbosch University. And it will be my pleasure to do the welcoming. And I want to start by welcoming our Vice-Chancellor and Rector, Professor Wim de Villiers, who on very short notice stood in for another colleague. Wim, thank you very much for being here. Of course, our guest of honor, our honorary speaker, Professor Riaan Combrinck. Riaan, sterkte. Dit is nou jou kans om jou merk te maak hier so by Stellenbosch. En vir die nie-ingenieurs ingenieurswese te verduidelik. Nee, dis altyd die interessante ding. We also have our vice deans here, Professor Celeste Viljoen, Teaching and Quality Assurance, and Professor Petri Meyer, our Research and Industry Liaison. We also have the Chair of Civil Engineering here, Professor Nico de Koker. We also want to welcome all the past and current colleagues from the Department of Civil Engineering, all the past and current students, the industry partners, the acquaintances, and all friends and family. And of course, some are here and others are online. So also to all the colleagues online, welcome to these proceedings. In particular, we would like to acknowledge and welcome Professor Combrinck's parents, Okkie en Rikkie Combrinck. So baie welkom hierso. En ook die skoonouers. Pietie en Madri van Sail. So baie welkom dat julle hierso is. And then also Riaan's two daughters, which I'm told are 4 and 7 years old, and I was said that I have to read this. I'm going to read this. Cara en Mia, welkom dat julle by julle pa se intree-rede is en dit bywoon, en ons hoop van harte julle kan stil sit vir die 50 minute. But then, of course, also Riaan's wife, Marieta. Marieta, ek hoop jy kan die kinders stil hou vir 50 minute. So, it's really always a very informative, auspicious, and but also a very friendly event, and we really look forward to the lecture from Professor Combrinck. We have a number of people, as I said, who are here, and then also a number of colleagues and friends online. I have been informed I have to make a number of announcements. The one that Jonathan Dale is very worried about is that there will be load shedding at 6 o'clock. Actually, Professor de Koker corrected me. The power will come on, which means the Jennies will dip and Eskom will hopefully rush in to fill that gap. So there might be a time when it will be a little bit dark, but we've made provision so that the lecture can actually continue during that dip, and even the streaming should continue working. I also tell you that you must please put your cell phones on silent, and the facilities for the ladies and the gents are, if you go out here and you turn to the left, there's a set over there, or you can turn to your right and there's a set for male and females on that side as well. So now it's my privilege to introduce Riaan to you. So Riaan is a valued colleague. He obtained his undergraduate, his master's and his doctoral degree in the Department of Civil Engineering here at Stellenbosch. Between 2005 and 2016, he was appointed as a full-time lecturer at the department in 2013. He has published 34 journal articles and 31 conferences, which means this promotion is actually quite late, because in other faculties they actually promote you with a lot fewer articles than 31. But congratulations on that. And then most of them were in international journals. Of course, that is very important for us. We have an international footprint of our research outputs. He leads the unit of construction materials at Stellenbosch University, where they support postgraduate students and also provide specialist consulting services to industry, also do some testing and the development of construction materials. His teaching and his research interests are construction materials with a special focus on, and I will not say cement, I will say concrete, Professor de Koker, on concrete. So Riaan, with that, the floor is yours, and please come and enlighten us on concrete.
Do I need to, must I stand here or must I put this on? Must I stand there? Sure. Okay. The multitasking is going to be interesting. Okay, so welcome everyone, and thank you for coming. I think the big privilege of this event for me is actually telling people, especially my family, my friends, of what I do. I told someone this morning I'm a bit of a box person, and when I get home, I'm out of the work box. So I don't think they know a lot of what I do. So I actually take this as a very special occasion to actually tell them what it is that I do when Daddy goes to work. So, welcome, and let's get into it. So the agenda for today is concrete, and we're going to look at the journey of concrete. We're going to look at the background, what is concrete, the history, where did it start, and some of the major milestones thus far, and then also where are we now, and take a step back and look at where are we now, and then the destination. I think the question maybe that you can simmer in your head is there an end for concrete? Is there a journey's end, or are you going to use it forever? So maybe think about that question for a while, and then the main challenge of concrete that is still remaining to be solved, and then some of the solutions. And then where does my research fit in? And what have I done so far? What is my arguments and my aims and so forth? Okay. So what is concrete? So concrete is a mixture of sand, stone, water, and a binder. And if you remove the stone, so the large aggregate, maybe let's get a pointer here. So if you remove the large stone, you end up with a mortar or a grout. Okay, so there's no stone. And as Professor van Niekerk said, and Nico told him, it's not cement. I know a lot of people call it the cement road or cement pillar. That's very bad. It's a concrete column. And then the binder is the most important part of this mixture. There's also a lot of binders that you can use, and we'll also look a little bit about that later on in the slide. And then admixtures commonly today is also used very widely in concrete, and there's a big impact on concrete, especially on the fresh properties. So I would almost say admixtures is the fifth ingredient you can really go without in concrete. Then the cement and the water reacts. When you add all of these ingredients together, it reacts, the cement and the water, and it binds everything in a hard rock-like material like this concrete dam. That's actually the Katse Dam, a picture of the Katse Dam there. So, and then concrete is extensively used. It's used in large infrastructures like this dam. It's also used in small everyday projects. And next to water, only next to water is concrete. So it's the most used material in the world next to water. Okay. So for the past century or so. So the fresh and the hardened properties of concrete are very important. In terms of the fresh properties, you need the concrete to be fresh, moldable enough that you can get it into the formwork that you build for it, and also in between all the reinforcing steel. And then it also needs to be strong enough to take the loads that is applied to it. And then very important, something that's often overlooked, it needs to be durable in the setting or in the environment where you actually place it. And concrete has actually proven to be durable. If you look at the Pantheon, which is almost 2,000 years old, it has stated testimony. It's stood for a long time. But I think there's some important lessons we can actually learn from the Pantheon if you look at how the Pantheon was constructed versus modern structures. The one thing is the concrete in the Pantheon is only in compression, concrete light compression. where it wants to be. So there's no tension forces in the compression. You can see in this dome of the roof, everything is just in compression. And that's very important because once you put it in tension, it starts cracking. Okay, and that's one of the reasons why modern structures add steel to your concrete, to actually take those tensile loads. Okay, but the Pantheon doesn't have any steel, and this is also one of the reasons why it's lasting so long, because once you add steel, with time that steel will start corroding. If it corrodes or rusts, it actually expands, the surface expands, and that cracks open the concrete, and is the start of big durability issues for concrete. Okay, then, yeah, it's also longer construction times. So we have, in modern days in the world, we want to do everything fast and cast quickly, and there's time pressures, and in those days, they built the Pantheon over 10 years. And when you do stuff slowly, you do it more thoroughly, and you do it more carefully, and you take more care, and the quality that you get is just more. And then also smart use of materials. So, for example, in the roof of the dome, they actually use lightweight aggregate to reduce the self-weight and actually help the load carry, or the roof carry the load more easily. So it's really the effective use of materials where you need it. So I think there's some very important lessons in that and why concrete lasts so long in the Pantheon. Okay, then some history. So evidence of concrete was used from 5000 BC to 5000 AD. And if you look at what they use lime, which is calcium oxide, with shale, which is clay, and in a mixture with some stone and gravel. And the lime would actually then absorb the CO2 from the environment and form calcium carbonate, which then binds everything together. The Romans actually took a big step forward, and they actually used a hydraulic cement. So this is a cement that actually hardens above air, or above water and in water. And that's very important. The lime previously only hardened in contact with CO2, with air. So they actually used the hydraulic cement, and they also used admixtures like blood and eggs and animal fat. So we think admixtures are some special stuff. It's been around for some time. So they mix this hydraulic cement, and that's sort of the key of their concrete technology. And it was from a volcano. The pozzolan material that they got was named after Pozzoli is a small town in Italy, and the volcanic ash that was erupted. They took that volcanic ash and they actually ground it, and that was the binder, the first cement basically. Okay. Then in the Middle Ages, a lot of this dramatic process of the Romans was lost, and they didn't use pozzolan and lime burning for a long time in the Middle Ages. And then we had to rediscover or reinvent cement in the Industrial Revolution about 1750 AD. And if you look at some of the early mixtures before it was patented, it all had to do again with taking limestone and clay and calcining it. In other words, burning it at a high temperature. And it was only in 1824 that I think it's an English bricklayer, Joseph Aspen, patented Portland cement. And this is the cement that we still use today. And it's produced by taking a fine mixture of limestone and clay and burning it at very high temperatures, up to about 1,400 degrees Celsius. And you need to get rid of all the CO2, which is also one of the issues with cement, but that is the CO2 that comes off, and that makes it a very, very strong cement that you get from it. Then some milestones sort of in the journey of concrete. The first one I would say is the first engineering use of cement to fix the Thames Tunnel with Portland cement. And this was actually the first breakthrough. You can see that this is an engineering material that you can use to great benefit. Then in 1854, they actually used it with steel. So this was the first time you could use concrete in a tensile environment as well by introducing reinforcing steel. And that was also a big breakthrough, because now you could start spanning large areas with steel where normally you needed a dome structure like the Pantheon. Okay, then I think a very important step in the history or the journey of concrete was the introduction of a rotary kiln. So now they could produce cement at a large scale, and they could start using it worldwide, all over. And I think this was also a major step needed for concrete to be used more widely. Then another aspect of it was when gypsum was added to concrete. Now, if you just have normal Portland cement and you add water to it, it hydrates very fast, and then you don't have a fresh time to actually, or fresh properties that you can actually cast it and vibrate it and so forth. So in the beginning, when they used concrete, they needed to be quick. It hydrated and set very quickly. But when they added gypsum, the gypsum actually retarded that setting times, and it allowed you about 3 to 4 hours that you can work with the concrete while it's plastic, and cast it and compact it perfectly. So this was also a very big milestone. Then I think with any type of material, as you start using it, you start finding out what are the defects, what are the problems with it. And I think this is also major breakthrough milestones in concrete's life. So when they built in France a free-span arch bridge, they started to see, but this concrete shrinks and there's cracks. Why does it crack? And I know if anyone sees a crack at home, they call the builder and they have to start fixing. But concrete shrinks. That's one of the things that it does. And if it shrinks and you hold it back, it starts cracking. Okay, and there's also things like creep. So in other words, if you sustain the load, there's increased deformation and so forth. So this is the first time I actually saw some of these behavioral traits of concrete. And this is stuff we need to know if we want to design and use it properly. Then another milestone was when they found out that the water-cement ratio influences the strength. This is an important milestone because now you can start designing concrete for a certain strength and then use it in the structure appropriately. Okay. Then another one was calcium chloride. They saw that calcium chloride attacks the reinforcing steel. And I think this is an important one because it sort of set the stage for durability issues in concrete. They saw calcium caused, or not the calcium, the chlorides attack the steel and the steel start corroding and you can't use the structure anymore. But it's also oxygen and water and all of those things that you need for corrosion. And this is a very important step that we found that it's not just designing concrete, but designing concrete that actually lasts. Then concrete was also used for major concrete dams in America, and the benefit to this is that this was the first time we could really build big structures that actually contains our precious water that we need to drink. And the concrete likes the water environment. So this is a very, very important use of concrete and why it is so successful as well. Okay, and then superplasticizers and plasticizers and admixture in general just open up a lot more applications for concrete. You could use it for any type of pumping up to 800 meters high, so it just made concrete more usable for everyone. Okay, so where are we now? So global society still greatly depends on concrete-like materials. There's no real sign of decrease in the use of concrete. So if you look at cement production in megatons, you can see from 2010 it's increasing slightly, and then there's sort of a plateau, but there's no decline in the use of cement all over the world. So we still greatly rely on cement and concrete-like materials. And developing countries also will play a big role here. I think China was the leading cement producer. India is slowly overtaking it. Maybe they've already overtaken them. But I think especially African countries is going to play a big role in the cement that is used because we need a lot of infrastructure and a lot of development, and concrete is the material to do that. Okay. So is there a journey end? Is there an end for concrete? Do we see in 1,000 years that we're not going to use concrete anymore? And I say no. Not as far as I can see in either case. I think the concept of concrete it's sound. It's yet to say. There's a reason why you say something is concrete. That saying isn't there for nothing. So, yeah, I think concrete is yet to stay. I'll get into what I think we need to change in a moment, but yeah, concrete is yet to stay. The concept of concrete is sound. There's no foreseeable alternative that really can compete with the advantages that concrete gives, and also at the volumes that is required to sustain the growth that we are expecting, or the use of concrete that we are expecting in the world. So some of those advantages, you can really use it on any site. It can be a big site or a small site, and you can use local materials. It can take any shape or size. If you can build a formwork, you can get the concrete in there. There's also numerous products and applications. If you think of, it's not just concrete as a structural member, but it's also mortar that you use to bind masonry. It's the grout between tiles. There's so many applications for cement-like materials, and it's not just the concrete industry. Okay, it's also resistant to water and other chemicals. I think our sewage plants is made out of concrete. It can resist that environment, and even things like our harbors close to the coastal areas, concrete is a material that we can use in those areas. It is resistant. It's strong in compression, weak in tension, but with reinforcing steel, you can use it in tension applications. There's also it also has a low cost compared to other materials. Okay, so what is the problem? Why is there so much pressure on concrete as a material in the world? And I think the way we have been driving this concrete vehicle it has been driven a bit recklessly and not sustainable. Megan, I maybe stole this photo from you in terms of traffic engineering, but we've been driving concrete a bit recklessly. We've been ignoring the green alternative concrete on the side and the warnings of people to slow down, stop using so much, and maybe even people coming out and say, but listen, you have to do stuff differently. So we've been driving it a bit recklessly. The way we produce use and think about concrete needs to change if we want to ensure that it has a sustainable and responsible future for us and our children. So, what is the main challenge remaining, I suppose? What's the elephant in the room? So, if you look at the way concrete is produced, you take limestone and clay, you make it in a fine mill, you take that fine mill and you heat it up to about firstly 900 degrees and then 1,400 degrees Celsius in a kiln. Then you get clinker, which is like golf ball size clinker particles, which you then mill in a cement mill with some gypsum, and then you get your cement, which you either in a lorry or in a bag. Now the problem is once you heat this limestone, which is calcium oxide, there's a chemical reaction where it goes to calcium oxide and CO2. So there's the main culprit. There's the problem. And that CO2 that's given off just by the chemical reaction. So we haven't even come to the heating of fossil fuels to get to 1,400 degrees Celsius. So that is the big problem. That is the elephant in the room for concrete and cement production specifically. So it's a large amount of CO2 that is emitted. It's about 8% of global CO2 emissions. I know there's the stat that says if concrete or the cement industry or the concrete industry was a country, it would be the first largest producing CO2 emitting country in the world. Okay. So 65% of those CO2 emissions just comes from this chemical decomposition of the lime, and then the rest is mainly due to the burning of the fossil fuels. Okay, but if you look at cement has a high carbon footprint if you produce cement. But when you combine it as concrete, in other words, once you add stone and sand to it, it's lower than most construction materials. So if you look at this table, you can see aluminium and reinforcing steel is up there with 12,000, close to 3,000 CO2 equivalent produced per ton of material produced. So CO2 equivalent emitted per ton produced. And the Portland cement is also up there. It's about 1,000, so it's quite high. But once you start adding aggregate, which is stone and crushed rock and limestone, which is quite low, you get a concrete, which sits about here, which is about 145. So concrete itself is sustainable. It's the cement that we are adding, which is the problem. So another thing about concrete that you need to keep in mind is concrete actually absorbs the CO2 with time. So it gets rid of the problem it created in the first place also. So it takes about 100 years, and that's the problem. But with time, if you take limestone, and this is the carbonation or the lime cycle, if you take limestone and you heat it up, the CO2 is given off, and then that calcium oxide, which is our cement basically, with water and calcium goes into calcium hydroxide with CO2 there from the air, forms calcium carbonate again. So it reabsorbs that CO2. It just takes some time. So the problem is that we are not giving concrete enough time to reabsorb this CO2, and we are using too much of it too quickly because we need so much. So that is the big problem. We've created concrete's biggest problem is that we use so much of it, and now suddenly because of the big volume that we are using, it's giving out of a lot of CO2. So the problem is the vast quantities and volume and the rate that we use it. So global and local commitments have been made to actually reduce CO2 emissions for the cement industry to zero by 2050. Quite the challenge, quite the goal. And given the expected use of concrete in the future, there's no way you can reach this CO2 emissions, zero CO2 emissions by 2050 by just using less concrete. Because then you will have to say people, no, sorry, you can't get a home, or you can't get infrastructure, you can't get a new mall. So I mean, it's not by using less concrete. So what do we need to do? So one of the solutions, I'm going to go through a few solutions, but one of the solutions is definitely in the cement production. And I think cement will need to change. We're going to still have concrete. Concrete as a concept is sound. You have a binder that binds rock and sand with water, and it binds everything together. But the cement that we use need to change. And if you look again of this production process of concrete, you can change the raw materials. So the lime that you use here, the limestone, we maybe need to start using magnesium oxide, which is in the mantle of the earth. It doesn't have any CO2 to it. So if you heat it up, there's no CO2 given off. And maybe this clay that we add here as well, we need to use a higher quality clay, that the cement that we get is a higher quality, and then we can use less cement to get the same strength. The fuel that we use, we are already burning tires, but we maybe need to use other waste materials in this burning process as well. Or maybe use alternative fuels like solar and wind to actually heat up and get the temperatures that you need. Also the milling process, what we use here to mill, we can add things like, I'll talk a little bit about it later, graphene and grinding aids to make that milling process more effective. So the cement companies really need to come to the party and actually change the way we make cement. Then carbon capture is also a big thing. If you can actually capture CO2 where it is emitted. I know there's a company that actually takes the CO2 and bounds it in pellets. So there's also a lot of potential there that you can get the CO2 where it is emitted. Then there's also other types of cement that we can use. There's this LC3 cement, which is a limestone calcium clay cement. And if you look at this cement, the reason why it has so much potential is because if you look at the clay deposits all around the world, there's a lot of clay. It's similar to limestone. That's why concrete is so successful, because there's a lot of lime all over the world and you can make it all over the world. And the problem with things like slag and fly ash, it's only limited availability, but clay is available worldwide. So if you take this clay, you don't have to heat it up. So the advantages of this clay, you don't have to heat it up to 1,400 degrees, so only about 600 to 800 degrees, so less CO2 is given off due to the burning of fossil fuels, and also there's no CO2 given off due to the calcining process. So if you just add 15% limestone and 30% calcium clay with this new type of binder, you can almost halve the amount of CO2 that is produced compared to a normal OPC mix. Okay, so what are some of the other solutions that we can consider? So better design, especially need to think of durability and not just make the concrete strong enough to take the loads. It needs to be durable for longer. And in terms of this, I think we've been designing for 50-year design life, and I think it's not enough. We must start aiming for 100, 200, 300 years structures, and not just 50 years. I think we're a bit short-sighted there, and we must leave structures that last longer for our children. Then also using thinner and more optimal elements. Only use the material where needed. The 3D concrete printing concept has a lot of promise there, and then also less wastage. So precast industry, 3D printing, there's a lot of less material that you can use to reach the same goal. Then also less defects, cracks, and other durability issues just shorten the life of the structure. So if you can get rid of those defects, you'll have a structure that lasts longer as well. Then the concept of circularity is also very important. We need to reuse and repurpose structures and materials. So if you have a structure, you demolish it, you reuse the beam, you reuse the column. The materials, you maybe crush it and you use construction and demolition waste as your aggregate, or you recycle materials from other industry. And also there's some alternative and underutilized materials, which I'll also mention in a while. Okay, so this is how the Global Cement and Concrete Association see it. So they're the one that made the big commitment of, with a lot of industry partners as well, that we need to reduce our CO2 emissions to 0 by 2050. And some of the solutions that they propose is efficient design and construction, efficiently concrete production, saving in cement and binders, saving in clinker production, carbon capture, decarbonation, and then also just the CO2 sink, the recarbonation of the concrete itself. But the point I want to make here, as you can see, it's not just one solution. There's not going to be this one wonderful solution and then it's going to solve everything. It's going to be a combination of a lot of different industries, a lot of different role players, and a different strategies, and all of them combined will actually make us reach our goal. Okay, so where does my research fit in? What have I done so far? So based on the arguments which I've sort of tried to make is that concrete is here to stay for the foreseeable future. And there's not a single solution that will solve everything, but rather several solutions, and that everyone needs to contribute. Researchers, producers, engineers, contractors, governments, and the public. Everyone needs to come on board. And based on that, the goal of my research to come and what I've done so far is to improve as many as possible aspects of concrete to ensure concrete's future. So, and the mindset that I have is that any improvement, even if it's a small improvement, if that improvement can be made, it can have a big impact on the long run. So if we're going to use concrete for the next 1,000 years, and we can make a percentage difference in this research over that 1,000 years, it contributes quite a lot. And then the sooner these improvements are implemented, also the bigger the impact. So if we find something now and we only implement it in 30 years, that's 30 years that is lost. So the sooner we implement these new research and solutions, the better. Okay, so what have I researched so far? So I researched into the main concrete constituents. So I looked into research in using water better, cement, binder, also aggregates. I research defects a lot, and also the weaknesses of concrete, which is cracking, alternative reinforcing, and compatibility issues, and then also a little bit of aesthetics and functionality. So time isn't that much, so I'm not going to go into too much technical depth, and I see my daughter's already sleeping, so I'll try and make it as light as possible. Senior Mia. So in terms of water, what have I done in terms of water? So we've been adding very small bubbles, nano bubbles to water. These bubbles are about 50 to 100 nanometers. So a strand of hair is about 50 micrometers. This is about 1,000 times smaller than a strand of hair. And these bubbles can be filled with air or CO2, and it's a stable bubble. In other words, it doesn't disappear. It stays there. It doesn't collapse or disappear with time. And some of the advantages we've been seeing is we're getting slightly improved flowability and strength with air. We're still working on it. I think we can get higher strengths, but that's what research is about. Then a very promising one is we're actually incorporating CO2 bubbles into the concrete. And that is a way of capturing the CO2 in the concrete. So getting rid of the problem directly by putting a high quantity of CO2 in the concrete. And then one I'm very interested about or excited about is the use of wastewater. So if you, for example, let's say as an application, if you're building a structure far away from potable water, you can use the water that is available there, the brackish water or the boreal water. You can treat it with these nanobubbles, and then you can actually use it, and there we save our precious drinking water. And we found that this nanobubbles actually neutralizes the effect of the contaminant. So if you think of salt, this is the strength with time, and you can see salt, which is chloride, often you find in brackish waters is an accelerator. So if the red line is the reference, and you can see the salt increases the strength because it's an accelerator, the solid line. And then the green one is sugar. Sugar maybe in sugar cane plantations in KZN, and that is a retarder, a natural retarder. And as you can see, it retards the strength development. And once you add the bubbles, it's this dashed line, you can see you sort of get rid of the effect that contaminant had. The retarder, it's not that retarded anymore, and the accelerator, due to the chloride, it gets back to the reference again. So it really neutralizes that effect and opens up the door for using contaminated and waste water in concrete. Then concrete, so in terms of the cement and the binder. So I'm going to discuss compatibility issues between cement and admixtures in a later slide, but for here it was mostly at the moment using nanographene. So this is another small particle. Nanographene is like a honeycomb-like sheet, and it's chemically bounded carbon atoms, and they have about a diameter, it's a hexagonal, but a diameter about between 5 and 50 nanometers. And it's a very thin platelet, we call it. It's about 1 atom thick. It's very light, stiff, and strong in a large surface area, but it's also expensive. But we add a very low dosage of it. So admixtures you normally add by 1% by mass of cement, but here we can actually add only 0.1%. And if you go and calculate the number of particles, that's millions of particles that you actually add, and actually more than the cement that you add. So small these particles. So there's potential to drastically improve concrete properties, but the practical application of this remains difficult because the particles are so small, they tend to flock together. So the real challenge is actually deflocculating and getting those nanoparticles all spread evenly in your mixture, in your concrete. So what we've done so far is mostly research on application techniques. We've been dispersing it in liquids, in the cement, also coating aggregates. We've been using it in combination with other nanomaterials, colloidal silica, nanocement. We're using it to improve the interlayer between 3D printed concrete and also just waterproofing of concrete. And we've had some better results, I think, but some of the initial results show that we actually couldn't get the compression strength that much higher. It's because this application technique, it's so difficult to get it right. But for all of them, for most of them, we've been seeing a big increase in tensile strength. So even if you get the application method wrong, you get the increase in tensile strength as well. So watch this space. I'm not going to say too much on this. We are working on it, and I have a feeling if we can get this right, it can be a big game changer in terms of cement and concrete industry. But we only started with this last year, so give me some time. Okay, then aggregates, so sand and stone as a resource is also under pressure. So the environment impact that you have due to mining sand and transporting it, I think in 2000 and this was, I didn't put the year, but I think it was in 2021, about 50 billion tons of sand was mined per year, and in that year. And then $1.5 billion of sand is also imported and exported. So some countries doesn't even have sand that they can use for construction. They need to import sand for their concrete. So we've been doing research in alternative sands, especially things like plastic, rubber, and glass. So here's a picture of the plastic and rubber and the glass. And you can see in terms of the compressive strength, if you add too much of the plastic, which is these two mixtures, the strength does decrease. If you add rubber, the strength decreases a lot. But things like glass does give you similar strength and often even higher strength. So there's some real potential in using that as alternative aggregates. And then underutilized sources, the desert sand. So this is also one I'm a bit excited about, but the third of the world's Earth's surface is covered with deserts. Now, desert sand has traditionally not been used in concrete because it has a single size, so most of the particles are the same size. And this makes it very unusable in concrete. So if you can find a way of using that sand as a concrete sand, you can use a resource that is really underutilized. So we've done some preliminary tests, and you can see this is the control and this is the slump. So the slump is indication of the fresh and workability property of your concrete. And as you can see, the red arrow shows that as you add desert sand, your slump decreases. So it's more difficult to work with the concrete. But as a remedy, if you look at the green arrows, as you add just a small amount of super plasticizer, you can get that slump up again to close to the control. Okay, so with some specific tweaks, you can still use the desert sand. And also in terms of strength, you can see the red arrow shows as you add the desert sand, the 28-day compressive strength lowers. But with a little bit of super plasticizer, you get the same strength that you need. So there's also some big potential there in using desert sand. Okay, so early age cracking was where I did my PhD in, so I did a lot of work on that. So this is the cracking in concrete in the earliest stage. Well, the concrete is still plastic, so before the concrete sets, 12 hours, normally 12 hours after casting, so it's really fresh concrete. And it's normally in concrete slabs like this, where you have a high evaporation rate and some reinforcing steel, which is your restraint, and that makes the concrete crack. And this happens very, very, very early, once you've cast the concrete. And there's two main types. There's plastic settlement. This is when you have reinforcing steel with it, and if there's no reinforcing steel, you can get cracks like this. And you can see the crack that you get with this early age cracking goes directly to your reinforcing steel if there is reinforcing steel. So it's really premature durability issues early on in the life of the concrete. So some of the things I've done here, I'm just going to highlight a few. So if you add reinforcing steel and without reinforcing steel, you can see the crack area with time is much larger if you actually add reinforcing steel and you have that settlement crack also contributing. But if you have no reinforcing steel, the cracks that you get are much smaller. Then the cracks are often not visible at the surface. But if you take a CT scan and you look at the concrete from below the surface, you actually see the crack is there below the surface. And then often when the concrete starts shrinkage due to drying shrinkage after 7 or 8 days, this crack then just opens and everyone thinks, okay, well, this is a drying shrinkage crack. But it's actually a plastic shrinkage crack that was opened much earlier. Then the influence of solar radiation. So if you test with and without sun, this is also very important because most models that you predict evaporation with doesn't include the impact of solar radiation. So we've done tests. Some of the nicest tests we've done with a view on top of the civil engineering building and with and without shade. And you can see all of this is the crack area with time. And these are all the concrete in the shade. And this is all the concrete in the sun. And you can see the big impact it has just having sun on the same mixtures in the same environment, how much bigger the cracks are just with sun. Okay, then tensile properties. This is something I did for my PhD. We had to test the fresh properties of concrete. And this is quite difficult because concrete is flowable. So we developed this mold that floats on an air bearing, like an air vacuum here. And then it floats on top of that. And you pull the two halves out of each other. And then you can measure the stress-strain relationship. And you can get the tensile properties of it and its behavior. And then you can model it to see how much cracking can actually happen. Okay, then preventative measures. We looked a lot at curing and fibers. So this is the crack area with time, and you can see this is uncured samples. And once you add a little bit of curing, this is normally curing water, you can see you reduce the cracking size, but also multiple curing and curing agents, you can even prevent the cracks completely. Okay, then also location risk based type analysis. We took what is the best approach to reduce these cracks if you're casting Cape Town versus Beaufort West. And we took hourly data, and statistically you find what is the evaporation rate at a certain time of day, and also based on the seasons. And based on that, you can say what is the best time to place your concrete. And you can also look what is the most influential weather conditions. So, for example, in Beaufort West, it's more temperature. So you must maybe cast in the middle of the, or not in the middle of the day when the temperature is hot, but maybe later in the day. And in the Cape, it's more wind. So there, using windbreaks is more effective at reducing the cracks. Okay, then 3D printing. So this is a nice thing about concrete. Once you think you've done your research, someone invents a new type of concrete, and then you have to test everything you've learned on the old concrete on the new concrete as well. So 3D printed concrete evaporates from all sides. It doesn't have formwork as a traditional concrete, and that makes it more vulnerable to plastic shrinkage cracking. So we were some of the first that actually tested this, and we also then looked at ways of preventing it. So if you add fibers, that's very effective. This shows the crack area with time, and as you add fibers, you can see you reduce the crack width to 0. And then also water curing and curing agents. Also, these are, I think, the red and the purple dots there. You can reduce the cracking versus no curing agents. So there is some remedies that you can use. I'm not going to go into the others. We used it too much now. Then just in terms of durability, what is the impact of these cracks and things on durability? So we took 2 samples, one where we allowed cracks to happen by restraining it, so cracks or interlayers slip, and one sample where we did nothing, so no potential for cracking. And then we tested the permeability, and the more permeable something is, the more the durability issues is going to be, because the more those aggressive substances enter. So, and as you can see, the restrained element which has cracking has a much higher permeability, so a much lower durability compared to one that has no cracks. Okay. Then we also looked at a model that actually predicts interlayer strength. And what this happens, as you go with your nozzle, you'll see the pass time differs. So as you print your concrete, the pass time differs. And if you leave the pass time is too long, you will have a lot of water that evaporates, and that influences the porosity and also the strength. And we've developed this model that you can predict the amount of surface moisture that is evaporated. Then you can see what is the impact on that interlayer strength that you're going to get, the reduction in it. Okay. Then alternative reinforcing, we've been looking at using textiles in concrete, especially 3D printing concrete as well, and then testing it and seeing how the cracks developed. And you'll see this is the load versus displacement graph. Just normal concrete just goes up and cracks, but once you add the textile reinforced concrete, you can see there's a much more tensile capacity that you can get from your concrete. We're also looking into creep of textile reinforced concrete, and then also using of steel fibers in concrete. Especially for pavements, so roads, steel fiber reinforced pavements, and what happens here, you have a big truck running over your concrete and it cracks the concrete. Now that concrete then actually is subjected to repetitive loading due to that truck running over it over and over again. And with time, the fiber only either slips out or pulls out or it fractures. And we had a look at that initial crack. If it was a big crack, your cyclic life, your fatigue life is much less than if it was a small crack. And it just highlights how important it is that our transport authorities actually get rid of those overloaded trucks, because it gives that initial high crack and it really shortens the life of your concrete structure. Okay, then compatibility issues. There's a big variety of cement and admixtures. Just look at this PPC cement. Depending if you buy it here, it has the same name. If you buy it in Cape Town, it will be this one with limestone. But if you buy it in Gauteng, it will be this one with fly ash. So there's a lot of different cements, even if it has the same name. There's also a lot of different admixtures. There's also imported cement. There's new type of cements coming on the market, and when you mix all of these concrete and the fresh properties, they often differ. So problems happens if you change the cement maybe midway or the admixture midway in the project. So you've been using this cement, you're going to use it for 6 months in a project. You've been using the same cement for 3 months. Then suddenly the cement is not available anymore and you use a new cement. Now suddenly your cement is it's not workable for 2 hours anymore, it's only workable for half an hour. Now suddenly you can't cast it anymore, so there's big cost implications. So some of the work we've done here is, this is just a base mix, a normal Portland cement mix, and this is the plastic viscosity. So this is how steep the mix is and how difficult it is to work with. If you add metakaolin to it, you can see the viscosity increase it. It becomes more difficult to work with. If you take that base mix and you add a plasticizer to it, you can actually see, well, the viscosity also increases, because often super plasticizers contains a viscosity modification agent. But if you take that same super plasticizer and you add it to the metakaolin mix, you can actually see, well, now the viscosity decreases. So often it's these unknown, unexpected events that happen, and you need to know that this is going to happen if you are changing your cement midway in your project. Okay, so almost finished. So aesthetics and functionality is also important. I believe if you have concrete that is more beautiful, it can be used for longer, and it can be more useful to society as well. So we've been adding paint waste to concrete, so it does decrease the strength if you use a lot of it, but it does give these white, and if you use a different colored painted white or green to it, so it makes concrete for me quite beautiful. Then also translucent or luminescent concrete. So this is for improved visibility in low light conditions, and also safety and warning functionality, and also functionality. So if you have, we added fiber optics to the concrete, and then if load shedding would happen now, we have a glow-in-the-dark aggregate in that wall that charged from the outside, and if load shedding goes off, we can hopefully see, because now it's emitting its light in here. So some of that type of functionality, and even using it as signs. This is a traffic sign we erected, and we charge it with either it can charge via the sunlight or maybe the lights of your car, and then it emits these light that you can actually see it when there is no light. Okay, so my research, it's just started. I've built on the research. I've been privileged to build on the research from the past, the current and past research community, and without them, it wouldn't have been possible. And as my mentor, Professor Billy Boshoff, said in his inaugural lecture, I think that was 10 years back. I'm not sure, Billy, but he said he loved concrete. And Billy, I also love concrete. I also love concrete. And if God wills it, I will continue to do research on concrete with my students for the next 30 years. So. I'm gonna do some words of appreciation, and I have to be honest, this was almost more difficult than the lecture itself. I've beat load shedding. Okay, but I think that the appreciations doesn't necessarily need slides, but we could maybe wait for it to come on again. Acknowledgments. Can I continue? Yeah. Okay, so I think the Dean, Wikus van Niekerk, Professor, thank you very much, and also the Vice Deans, Professor Petri Meyer and where's Professor Celeste Viljoen, thank you very much. I think your leadership, I realize how much time it takes if you go into the admin side of it, so your leadership is really appreciated. And then the following 4 groups of people in the civil engineering department, and I specifically didn't want to mention name because I'm scared I'll miss someone. So all the laboratory staff, I think your assistants in the lab with the tests and all of those things, I mean, without you, there's no way I can lift all that concrete. And then, and also my students. And then the administrative staff for their general assistance, but also specifically with finances for students and the postgraduate administration. I think you know who you are, but thank you very much. And all the academic staff for being a soundboard, for your teaching and research support. It's really greatly appreciated. And then past and current HODs of the civil engineering, there's a few of them around here. Thank you very much. I realize how much time and effort goes into, it's like your new set of students that you have as academics, and thank you very much for mentoring us and offering up your own research for that. It's greatly appreciated. Then some of the industry partners for their financial and material and also technical support. So Fine Bubble Technologies. I don't see Paul here, but thank you very much. Criso, Anthony, Sika, Penetron, PPC, and also Glade Chemical Manufacturers from Barry. Thank you very much for all of your assistance and help. And then the National Research Foundation of South Africa and also the Wilhelm Frank Trust. I think also financial supports of especially postgraduate students. It really can't be, it's very, very valuable. And then all past and current students, from vacation work students to final year students to masters, doctoral and postdoctoral students, you are really the heart and soul of the research. And without you, none of this research would be possible. And if I can have one wish after this, is that I can have enough money to give bursaries to all of you forever. So, then to Professor Billy Boshoff, he's now at University of Pretoria. I won't hold that against him, but he was really my mentor. And thank you very much, Billy, for being my academic mentor. Then friends and family for your support and encouragement. Hopefully you know a little bit of what I do now as well. And then my parents and parents-in-law for your unconditional support. My daughters, Cara and Mia. Thank you for making life exciting and busy. Dat julle lewe besig hou en baie opwindend. And Marietta, thank you for keeping me humble and making every day an adventure. And then finally to God, for all the abilities and talents, really without Him, none of this would be possible. Okay. there is some time for questions. I did rush a bit there, so please ask questions. I did hear that was the first time anyone ever allowed questions to be asked, so maybe this would be the last time then as well. So.
I've got a question about that. So you said that concrete can reabsorb CO2. Does it change the properties when it does that? So is it not a good thing for the concrete itself?
It's not necessarily a bad thing, but one thing that it does change, if it goes to calcium carbonate, it lowers the pH. And it's called carbonation. Yeah, it's called carbonation, but that lowering of the pH actually destroys the natural protection of the concrete towards the steel. So if a lot of carbonation does happen, you lose that protective layer around your steel, and then the corrosion of your steel actually starts happening quicker. But it's not necessarily in terms of strength. It's more in terms of that durability aspect that it brings towards it. Yeah.
Use of seawater.
The use of seawater. So that is actually one of the things that Bianca, she's sitting there. She went to Bloubergstrand and used a lot of seawater in her mixture. So I don't think full seawater. Maybe with the nanobubbles we're going to try. So one of our mixtures is actually half seawater, half normal water. And we'll see what happens, but we found some very promising results. A lot of times you still have to, you find out the compressive strength and the fresh properties is okay, but then you have to do the durability properties as well to see whether it's going to last in the long term. So you can't just, so we've sort of started with the compression and those things, and it shows potential, but you still have to add steel to it, and then you have to see what's happening. So there's a few phases you have to go through, but there's potential. Well, the interesting thing, if you look at the precast industry without steel, they've been adding table salt as an accelerator naturally. So if you don't have steel, you don't need, you could use seawater. That's maybe something they've been overlooking. But seawater also contains other things, not just salt. Yes.
I have a question. So you mentioned the Romans, and I did a bit of research on Roman concrete, and it's like I get this thing because it grew stronger in seawater. If it's such an amazing concrete, which obviously produces amazing structures, are there any reasons being made to kind of find that recipe back?
So it's a good question. He's asking about the Roman concrete. So this is interesting. So you need a volcano to get the volcanic ash. That's the one problem. The interesting thing is, the thing with a volcano, it's an igneous rock, but the only difference is it's been expelled to the air and it cooled down quickly. And it's that fast cooling down process that actually makes it reactive. The interesting thing is all of the igneous rock that's been formed under the earth, that with time, that igneous rocks and metamorphic rocks, they weather. And that actually gets a sedimentary rock, which is clay, which is the metakaolin that we then actually heat up to form metakaolin or calcium clay, which we are now proposing as the new cement. So we sort of have reinvented it, but we are not using the volcanic ash. We are using the weathered granite and things like that and reheating it up again, and then we sort of have a artificial volcanic ash that we're using again. Mia, kom, skiet met 'n vraag.
So you mentioned that you think structures should not have lifetime of 300 years. So that you, as a structural engineer, that would mean that you have to design it for for much larger loads, which would make your structure a lot more powerful and more.
It's a good question.
Maybe the solution is to make them shorter lifetimes.
So I think it's better if you have a longer design life, do you end up with structures that are more bulky? And I think then you're looking at it wrong because it's not strength that we need.
So I said that.
Yeah. It's actually concrete that doesn't allow things to enter it. So you can still end up with a concrete with the same thickness. You just need to make sure that oxygen and water and chlorides doesn't go into it. So if you end up with something bulky to have it last longer, then you've done it wrong. You need to look at making it more durable in terms of what is causing the durability issues. Okay. So I think I'll come and knock at one of my colleagues, Professor De Kooker's wall, when we get to the statistics about all of that 50-year design life, 100-year design life. But yeah, I think we're missing an opportunity to actually be designing structures, it needs to last longer. We're already doing it for hospitals and critical structures like that, but I think we are missing an opportunity to make structures that last longer. That's a testament for concrete. Like the Pantheon, I mean, 2,000 years later, I'm still lecturing on it, so I think we're missing an opportunity. Yeah. Yes?
What about the radioactive shielding capacities of concrete and looking at that in standard housing? Of course, we're exposing ourselves more and more with climate change and with the impossible fact of nuclear war breaking out.
So,
Using that to protect
yeah.
life.
They say if you don't exactly know the answer to a question, you say it depends. And I think it depends in this, but it's a good question. I haven't gone into that field. I think but there's a lot of different scales that you can use. So he's asking if radioactive material, can you use concrete to shield it? I know concrete is actually very good at using that. They increase the density, so use a high density concrete and actually gives better shielding. But yeah, research into that is interesting. It's stuff that we need to do. I need to get some ethical clearance on using radioactive material in the lab and exposing the students to it. But yeah, so I think there's definitely potential. I think concrete is a material to do it, especially because we're using it all over the place. But exactly to do the research on it, yeah, it's something I haven't gone into. But there's definitely potential. Yeah. What is
You use different cement. What is the risk?
I did test the concrete of the Klein Willem Dam about 10 years ago. So the biggest issue with the Klein Willem Dam is they haven't started building it. That's the biggest risk there. They've done all the tests and all the designs a long time ago. It's just politics is the reason that hasn't been built. Well, I don't know. Actually, I don't know. Take that statement back. I don't know. But the biggest problem is they haven't built it. The engineering behind it is sound. They can go for it. It's actually the oldest dam in South Africa, Klein Willem Dam. Okay, I should stop.
So, ladies and gentlemen, I'm Wim de Villiers. I'm the Rector and Vice Chancellor, and it's my honor to respond to Riaan here. Riaan, well done. That was really inspirational, and it was fun to listen to. So, one of the highlights of my academic year would be graduation ceremonies, right, in March and April, and it's capping those students and then walking across the stage and with the joy of the families, and that's a true highlight. And another element of these graduation ceremonies would be awarding a PhD degree and capping a PhD student after hard work, long years of long hard work. And that's the height of academic studies, in a sense. And then embarking on an academic career. And an academic career, as one should realize, is not a sprint. It's not a sprint. It's a marathon. And here you are. Here you are. Well done. So, a full professor, and what would full professors do? They profess. They profess. And I think what we've heard here this afternoon is the breadth of Professor Combrinck's expertise. And I must say, I've in my time as Vice Chancellor, I've attended quite a few inaugural lectures, and I think the one that comes to mind is a professor in Afrikaans Dutch, in Afrikaans, who gave an inaugural lecture on the history and used many examples of vloek in Afrikaans. So die geskiedenis of swearing in Afrikaans. So die geskiedenis en baie voorbeelde van vloek in Afrikaans. And that was certainly memorable. Well, this was also very memorable. So I'm not going to pretend that I know anything about concrete. All right, I'm a gastroenterologist by training. I'm a physician by training. So, but what I did learn and what I did see and witness here is in your professing and in your expertise is the passion and the love for concrete. I definitely picked that up. I also picked up that concrete equals job security. We're going to have it around for a long time. I learned about the Pantheon. I learned about the Romans who used blood, eggs, and animal fat and as binders. And so as a physician, that appealed to me. I also wondered, as a physician, the phenomenon of early age cracking. Now, as a physician, I would just refer it to a plastic surgeon or inject Botox. Botox would be also work very well. And then I've just come back from the States where I attended a gastroenterology conference, the preeminent gastroenterology conference in Chicago. It's your worst nightmare, all right? It's called Digestive Diseases Week. So it's more than 15,000 gastroenterologists together. So I think I just heard about my next biggest nightmare, which is the Global Cement and Concrete Association. That must be a bunch of giggles, That must be a lot of fun. So, not knowing anything about concrete at all, I did exactly what students nowadays would do, and that is to go to ChatGPT. All right? And I said, okay, concrete construction, typed in concrete construction and humor. All right? So, came up with this. Concrete. The building material that's basically the Chuck Norris of construction. Picture this. It's like the bouncer at the nightclub of architecture. All the other materials try to get in, but concrete stands there, arms crossed, saying, hold on a second, let me check your strength, durability, and reliability before you can come in. And believe me, hardly anyone passes the concrete test. So that was ChatGPT, not too bad actually. So, Professor Combrinck, congratulations, well done, and really, I really admire your passion. Well done.
Good evening, ladies and gentlemen. So it's my pleasure to just do the acknowledgements for the evening. The first person I think that needs to be thanked is Riaan for putting a lot of effort into giving us this lecture. So Riaan is in my experience, a reliable and a steadfast member of our department. And I hope he is in the department for the next 30 years. So thank you, Riaan. So then also Prof. de Villiers for taking care of the ceremonial part of the evening on short notice. Thank you for coming. And then I want to make a point of pointing out our laboratory staff, who Riaan also mentioned. They work behind the scenes and they are an integral part of the work we do in the department. So specifically, Charlton Ramat and Leroy Jones and Julian Thompson, they work very hard and they deserve to be mentioned. So thank you to them. And then on the side of the registrar's office, the people who were responsible for arranging this evening was Jonathan Dale Blankenberg, Olivia Adams, and Amira Brown. And then from the Dean's office side, Ulrich Smith and Clint Puerta did a lot of work to get the venue ready for the evening. And then finally, Justin Alberts, who's sitting back there quietly, is responsible for the video recording and the live streaming of the lecture. So thank you. Then you're welcome to join us for drinks and snack afterwards, and I will not stand in your way from enjoying that. So thank you for coming.